All right, picking back up here. I'm gonna take a second because again we're about to get into some really interesting things. Let's open this one up. What we got searching code injection in the auto assembler. Byte type. Do we have anything else interesting in here that we can maybe get in? Yeah, we're gonna use that, but we'll go here. All right. Originally posted by Scribbly. Let's say you found the code that decreases your health. Problem is that it seems to also affect the health of your opponents, and somehow you can't seem to find the base pointer. In those cases, doing some code injection using the autoassembler is the easiest solution. There are several ways that code injection can help solve this problem. One method is finding another code that accesses your health, but does it only for your own health. For example, the code that is used to display your current health. At that point, you can inject some code that stores the address of your health to an address you can find. Again, the grammar here is not super. Then in the code that decreases your health, inject some code that checks if the address changes is the address or that. Okay, so starting over. In the code that decreases your health, inject some code that checks if the address that is changed is the address stored by the other routine, which is referred to up here. If it is, skip the code because we stored the address of our own health. Otherwise, we know it's not our health, so just decrease the health. Or even create an instant kill cheat by decreasing the health of the opponents by a really big value. This is a popular method, one which I use quite a bit myself when I'm sort of messing around myself. I just find my health value in a game. I don't care, whatever the game is. It's a float, it's a byte, 4 byte. I don't even care. I just find my health, make sure that it's my health, and then I just find out what writes to it, find out what accesses to it, and I get to a point where I found the routine that modifies health values in the game. And we'll talk more about generic routines in just a little bit. We're going to write that down here. Generic routines that modify value or modify player enemy values. Just as a reminder, because I am, enjoying a bit of the sauce. So this is a popular mechanic that is used because when you find the routine that modifies health, you can create a check that differentiates between is this the health of the player or is this the health of an enemy. And if it's not the health of the player, then you just invert the value of whatever the current enemy or opponent's health is. And when you invert it, you're essentially just subtracting whatever their current health is from their current health. So if you're saying, well, I want to subtract some value or I want to subtract some value from the opponent's health, all you do is you change that instruction to say, I want to subtract the, or I want to add, as the case may be, the negative value of my opponent's health to whatever their current health is. And you have a dynamic way of saying, set their health to 0. It's as simple as that. So now the auto assemble script part, this is where it gets really kind of crazy, and there's no explanation for any of this stuff above it. You could dig around here and maybe get it, but again, some of it is not super clear. Let's say that at 00405000 is the code that reads your health, and there's some assembly instruction here. And at 00421000 is the code that decreases the health of enemies. Some more instructions here. First, allocate some memory to place your code in, and to allocate space for variables. Use alloc name size for that. Alloc allocates a region of memory with read, write, and execute access. Be aware this won't work in Windows ME 98 or 95, so please upgrade if you were using those ancient operating systems. That right there is good advice. So, code. You have code here, you have code here, you have code here. None of that is doing us any favors because we don't really understand. For the purposes of what we're talking about here, we don't even know how to write assembler yet. So let's see if we can maybe get into that a little bit. Let's go back here to the basic assembler thing. Some examples: sub, blah, 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 blah. Argument, the values. Let's take it apart in its most basic elements. Opcode, parameter 1, parameter 2. What's the opcode? The opcode is sub. What is parameter 1? It's EBX. What is parameter 2? It's EAX. The opcode is the instruction telling the processor what to do. Let's sort of just stop right there and say that opcodes exist so that, well, first we're going to bring this up to make sure we're not running out of time. Opcodes are the most basic functionality that we will ever deal with when it comes to telling the processor how to do things. When you are giving an opcode to the processor, you are essentially feeding it some bit pattern that says, that instructs it what the next instruction it's going to, see if we can rephrase that. When you feed an opcode to the processor, you are telling the processor what the next instruction it's going to apply. Okay, we're going to rephrase that again. When you feed an opcode to the processor, what you're doing is you're instructing it what the next operation it's going to apply to the next set of parameters it receives is. So when you feed a sub opcode to a processor, it is going to change its, or it's going to prepare itself to subtract parameter 2 from parameter 1, or parameter 1 from parameter 2, depending on the architecture. But for our purposes, we will say that that it will subtract parameter 2 from parameter 1, because I want to say that this is based on x86 assembly, and that's what so we're just going to assume that generally it applies when you give an opcode to a processor, it's going to apply parameter 2 to parameter 1, however that makes sense in the context, and we'll see that as we start talking about other opcodes. So keep reading. The opcode is the instruction telling the processor what to do. We just talked about that a little bit. In this case, it'll decrease the value stored in register EBX, which is the first one here, with the value stored in register EAX, which is the second parameter here. In this case, EBX equals 5, as up here it's just some long string with leading zeros, but it's essentially 5, and EAX is 2, so it would be 5 minus 3. EBX after this instruction would be 3. So there is some subtlety here, because what happens is when you do a sub operation, and with many of the opcodes that you'll give to a processor, you will sub the second parameter from the first parameter. And if anyone has any sort of experience with Python or any programming language in general, you'll sort of have an assumption of a return value. And that does exist to a certain extent if you're getting into complex things. And there's actually some statements that you can use to, push return values on the stack and things like that. We're going to sort of shy away from some of that real crazy stuff, but for the sub opcode and the add or the move and some things like that, basically what you're doing is you're taking the second parameter, you're applying that relative to the opcode to the first parameter, and then that value is automatically stored in that first parameter. There is no return value per se. It's just here's a value, subtract it from the first value, and then make the value of that first register, more importantly, whatever that value, whatever the result of that calculation or operation is. Also note that whenever you see an opcode with two parameters, the first parameter is the target of the instruction, the second is the source. We pretty much just said that, so let's just harp on this a little bit more. We have a simple, very simple string or assembly instruction here. We have an opcode, we have parameter 1, we have parameter 2. So what is happening here? The sub opcode is being fed to the processor. The processor is essentially saying, all right, give me the parameters, I'm ready to do subtraction. So then you feed in EBX, EAX, and the processor is saying, okay, I'm going to take the value of parameter 2, I'm going to subtract it from the current value of parameter 1, and then I'm going to store the result of that operation in parameter 1, and whatever the original value of parameter 1 was is obliterated and lost to time. And now that's not true, because you can always store the value of whatever EBX is before you do the sub, but that's up to the programmer, and the computer won't necessarily implicitly do that for you. So that is sort of the essence of how an opcode is examined. or how an operation is performed in assembly. Now, EBX and EAX are probably, if you have no experience in these kind of things, are just, you're asking yourself, what the hell is EBX? What the hell is EAX? Are they variables? They are variables in the sense that you can store values in them and then refer to those values dynamically without having to constantly retype them or do some, rolling calculation throughout your program. They are sort of the original variables, if you will, because what's the best way to describe this? How do we want to proceed from here? We're gonna go here. We're gonna close that. We're gonna go to this. We're gonna ask Wikipedia, what's a register? Computing. All right. In computer architecture, a register is a small amount of storage available as part of a CPU or other digital processor. Such registers are typically addressed by mechanisms other than main memory, or absolute memory as we referred to them in the very, very, very beginning of the series, and can be accessed more quickly. That is sort of the defining element of a register right there, is that register access is extremely fast, much faster than going into RAM. Almost all computers load data from a larger memory into registers where it is used for arithmetic, manipulated, or tested by some machine instruction. Manipulated data is then often stored back in main memory either by the same instruction or a subsequent one. Modern processors use either static or dynamic RAM as main memory, the latter often being implicitly blah 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 caching. Yep. Let's see if we can maybe get into something here. Categories, some examples. This table shows the number of registers mainstream. FPUs, I don't want to get into that quite yet. All right. But this Wikipedia page here sort of, if you want to read more, you can certainly jump in there and hop right into it and whatnot. But for our purposes, we've sort of proved the point, or sort of made the point, as case may be, that registers are what we are going to. Is it all that we can use when we're stuffing values into when we're trying to operate on or perform operations on values? Yes, because in order to do, there are certain limitations, and I'm being necessarily hesitant about saying yes, because there are some operations where it is not valid to use. Sometimes you could not subtract. I don't know. Let me just stop and read on here. They have to get into it at some point here. The second parameter is the source. Yada 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 yada. Just a sub. Like ink and deck, we get that. Right now, 32 bits. Yep. 64 jump loops calls. We'll get into all that. We have ret, call stacks, flags, overflow sign. All right. So what we're gonna say here is that when you're messing around with these registers, there are occasional limitations with how you can push a value or move values in and out of them. Sometimes in order to perform a certain operation, you have to have the value in a register instead of just in some memory location. And there's a whole lot of sort of subtlety that goes along with that, but see if we could maybe immediate values. Easy that bit, sure. Main forest registers contain values, information to keep, and now we're new to ASM. Let's take a look at the main side, yada yada yada. Constructed. We'll get into all this. It's a lot to take in. Yeah, it certainly can be. Let's discuss GP registers. All right, we're gonna stop here, and we'll come back in right here and see if we can maybe quantify this a little bit, or maybe clear this up a little bit better.